Okay, hey guys. I am going to do some of the notes here, not the examples though. I'll send you a message about this, but I'm going to do basically all of the notes that are non-example related, and then in class on Tuesday we'll do the examples and the checkpoints. So I'm going to extend the deadline for the checkpoints because I realized after I assigned them that we really hadn't done any practice with that, and I wasn't sure if maybe you needed some more practice before you were able to do those. But if you already did them, that's great too, because you do need to do them. So, all right. So I did say if you were absent, I'm just gonna kind of like show all the pages of this, so you can kind of pause if you need to. Otherwise, feel free to fast forward a little bit, but this shouldn't take long. Okay. So here's the second part. I think that gets everything. Right, and then the next part where it's a little bit messy and we decided to skip that simulation. Okay, there we go. And then this is where we left off in class. So, excuse me, talking about the conditions for regression for inference and how do we check them. This is linear regression, just like so we know. All right, and so we do need to know, is it linear? Because in order to do this linear regression for inference, it has to be linear. And there are a couple different ways that we can check that. We can just kind of look at the scatter plot and say, is the overall pattern linear? Sometimes it's really easy to tell, sometimes it's a little bit iffy. And if we were in class, I would ask if you remembered anything from chapter 3 that would help you with this, and hopefully somebody would say, that says is, sorry. Somebody would say, check the residual plot, right? If it's a good linear fit, then the residual plot would show no pattern. If there's any distinct pattern, if the dots on the residual plot like form a parabola or something like that, then linear is not a good fit. You want about the same number of dots above and below. Anyways, I won't get too much into that because you should already know that. So, does then just like every other test we've done, we have independent. So for independence, that's 10% with sampling and just random assignment for an experiment. So let's say I should probably use a different pen. This one takes up too much space. Oh well, we're gonna power through. All right. Check for normality. So for any x value, y's vary in a normal distribution. So check for skew or outliers in the graph of your residuals. Okay. The residual plot shows your graph of the residuals, but Okay, so the other thing that we have to check that's a little bit different, standard deviation of y is the same for all x values. So we need equal standard deviations. Basically, the way that you can check for that is looking at your residual plot. You want to see if the vertical spread is roughly symmetric. So what I mean by that is the residual plot, just if I have a piece of scratch paper to kind of show you, you want a residual plot that shows no pattern, right? And you want the distances to be about the same on average from the top and the bottom. Okay, so it's not like a perfect example, but kind of to give you an idea of what we're talking about, we want the residual distances to be roughly symmetric, like from the top to the bottom. Okay, so sorry, residual plot, not residuals plot. So it should be hopefully that made sense. The last one is random, which we kind of already said, so I'm just gonna kind of put it down here and not really say much. Okay. Okay, what are the 3 parameters in a regression model, and what statistics do we use to estimate them? So I'm going to make kind of a little chart similar to what we've done in the past to talk about like mu versus x bar and all that stuff, the parameter versus the statistic. So let's see. One parameter we use is alpha, and that's the y-intercept. We've already kind of talked about this stuff, so I'm kind of just going to blow through this. But and the way we estimate that is with A, the statistic that corresponds to the y-intercept, and beta, which is the slope of the regression line. We estimate that with a lowercase b. And sigma, which you already know. And just as always, we estimate that with s. That part hasn't changed, okay? What is the standard error of the slope? Is this on the formula sheet, and how do you interpret it? So SE of B is equal to the standard deviation of the statistic divided by the standard deviation of the sampling distribution times the square root of n minus 1, and it is on the formula sheet. Okay, so this would be that S sorry, that's an S. So S is the sum of the residuals squared. I need white out, sorry. So the sum, carrying on our Greek letters, that is a capital sigma. The sum of the residuals, okay, sorry, squared. So kind of like what before, but okay, over n minus 2. And how do we interpret it? Okay, so obviously always in context. What it is it measures how far the estimate is from the truth in repeated samples, or the truth or the parameter, or however you want to say it, the true value. We can say of the true value, the population parameter, whatever. All those things are kind of the same. Hopefully you can see all of that. Let me move it up just to make sure if you need to pause and write any of that down. Okay. Okay, so for the seating chart experiment that we talked about in class, okay, the seating chart experiment that we talked about in class, state and interpret the standard error of the slope. So the standard error of the slope we already had. It was 0.9472. Okay. So if we repeat this random assignment many times, if we did the same thing, right? So for a bunch of different tests or a bunch of different groups, if we had a whole bunch of different samples, a whole bunch of different classes, statistics classes, in order to do this experiment on them, and we repeated this entire experiment many times, right? That's a sampling distribution, and we took basically the averages of all of our results. That's what we would be finding. And so let me just write that a little bit more coherently than what I said, and I'm sorry for the mess right here, but just do that. So if we repeat the random assignment many times, or I could say the randomized experiment, I'll say that. The slope of the estimated regression lines would typically vary by about this much from the slope of the true regression line for predicted test score from row number, right? So that's the context part. But basically we're saying what we said just a second ago on the bottom of the other half of this page. But yeah, so if we repeat this many times, the slope of the estimated regression line and we'll say approximately right, that little squiggle means approximately. I hope that side of the page said. Yeah, it is. From the slope of the regression, like the true regression line. For a predicted test score from row number. All right, Any questions? No? Okay. I think this might be the last thing I'm going to do. I'll flip through the rest of it and make sure that we're clear. But all right. So what is the formula for constructing a confidence interval for slope? Where do you get the value for T star, and how many degrees of freedom should you use? All right. A confidence interval for B is equal to B plus or minus T star times the standard error of B, which we wrote the formula for on the previous page, so I'm not going to write it again, right? All right, so the confidence interval formula is on the formula sheet, but it's in words, right? So for a confidence interval, it's always statistic. I'm sorry, I don't have a formula sheet with me to show it to you because I guess I can find it. Whatever. You guys know. We've been doing this all year. It's statistic plus or minus margin of error, or statistic plus or minus critical value times standard error. Okay, right? This whole thing, T star times standard error, that's the margin of error. And just this piece is the standard error, right? So the statistic, we also have called that the point estimate. Right? Because that's the value you actually got, but you know that it's not likely to be the exact answer. So anyways, that's why we also call it a point estimate, but we've used that term before. This is the critical value. Remember, our critical values are always Z star or T star. And then this is this whole thing together is the margin of error. And so that's the way it's written on your formula sheet. It says statistic plus or minus critical value times margin of error. I believe it says it in words like that. Okay. So you can use a command in your calculator in order to get T star. You can do T star. You can also use the table, but we're going to go ahead and pretty much do everything in the calculator at this point to avoid error. So when you do inverse T, this is under the distributions menu. I don't know where to say that. I'm sorry, I don't have a calculator with me either. Should be under the distributions menu though. We'll practice this in class together though. And then what it's going to ask you for, you're going to put in the area and degrees of freedom, which again we'll talk about more next class. But and your degrees of freedom here are n minus 2. So easy formula for degrees of freedom, it usually is. And that's about it. Okay, so let me see what else we have. All right, so the next part is an example for a confidence interval. I'd like us to do that together in class. So I am going to hold off on that. Do I want to go ahead and talk about significance test? Yes, I do. Okay. All right, so for significance tests for beta, it's which is the slope of the regression line, right? What is the standardized test statistic for a significance test for slope? Is this on the formula sheet, and what degrees of freedom should you use? All right, so for this, you're going to use H null is that beta is equal to beta null. Oh, oops. And then let me see, your T, so your test statistic is T, and it's going to be your B, so your sample slope, minus the claim over the standard error of B. And again, that formula for standard error of B is on the other page. And then with that, we'll use degrees of freedom, n minus 2 still. So that hasn't changed. I don't think it says it. Right, so whatever they think or whatever they're claiming, that'll be the hypothesized slope. And so depending on the context of the problem, just like in any other section we've done with these, if you're looking for what's above the t, then your HA is going to be that beta is greater than beta null. You could also have that if you have a negative t, generally you're going to be looking below. And then your HA would be that beta, is this in there in the screen? Okay. Beta is less than beta null. And then also we are bringing back the two-way, so we couldn't do that with chi-squared. But there are cases where it's just a not equal to, right? And so that gives us a not two-way, two-tailed. Shouldn't say two-way because that makes us think that there are many variables. Okay, so beta is just not equal to beta null, okay? All right, we didn't do this example, so we're not gonna do that. All right, let me just look through and see if there's anything else I wanted to talk about right now. No, the rest of this, so we'll do these two examples together in class, and you should have time to finish your checkpoints as well. So anyways, I hope you enjoyed the video, and just for you, Pedro, I'm gonna go ahead and say that everybody should like and subscribe. Thanks.